Hello. Recently I showed you how to simply get FLEUR, how you can download the binary and just start running immediately. Today I will show you how to actually compile FLEUR yourself. This has a few advantages. You can include more libraries that make it faster, and you can also include more features, and you can optimize it for your specific machine, which if you have a very large calculation, you're going to want to do this. So first things first, we have to get FLEUR, and to do this you go to our website and then you click on downloads, which brings you here, and then you go to the FLEUR GitLab. And this is where we do all our development, and here you can simply clone our repository, and you can just simply type git clone, and then you add our link as you would do with any other package. And if you go into the FLEUR folder, you'll notice that you are in the development version, which is our default branch, but there's a number of other branches. For example, you could go to the stable branch, which has more updates than the release branch, and then there's a bunch of feature branches. You could also go to one of the older snapshots. And with this, we can actually start compiling FLEUR. Now I included a few hiccups to show how to circumvent these hiccups, but a normal FLEUR installation should be much easier. So if you type /configure -h, you can see the options you can give to this file. So among them, you can specify a CMake package, you can load some external libraries, which I'm going to show you later. You can actually label your builds, which is quite helpful. And you also have the external feature. And most importantly, you have the environmental variables that are used for most compilers, FC and CC. So we simply want to build FLEUR, so we just type /configure. And on most systems, this is going to work. But on this system, it turns out this computer has an old CMake. So we actually need to find a newer version of CMake. So we just simply type -external CMake, which downloads a very up-to-date version of CMake from the internet, and then uses this instead. So here's the second hiccup. It turns out that this computer also has a very old Fortran compiler, or that CMake finds a very old Fortran compiler on the system. And so we have to specify the Fortran compiler that we wanted to use. And so what we can use is simply type fc equals gfortran cc equals gcc /configure -external CMake. And now it actually already has CMake, it doesn't download it again, so this is much faster. And now you can actually build FLEUR. So you have XML, which most Linux systems have out of the box. You have LAPACK, which oftentimes you have to install over your package manager. And you don't have anything else. So you can build the sequential version, the serial code. And you say, all you'd have to do is you go into your build directory and you type make. I'm not going to do this because I want to do some more advanced stuff. Namely, we're going to configure it again, and we're going to give it some name. Let's just call it MPI. And for this, we need an MPI compiler. And the MPI compiler I have on my system, you can just type MPI tab, and it will suggest some to you. And I'm going to use the MPI ifort. So we type fc equals to MPI ifort cc equals gcc /configure -external CMake -l MPI, that's the label. And additionally, I'm going to include libxc, where you have to simply type libxc true, and this is going to include the libxc library that provides a large amount of exchange correlation functionals, and most of these work in FLEUR, but I'm going to make a future video about this topic. So if you run it like this, it will download gcmac again because it's a different build directory, and it's also going to download libxc. So now it says it can't find libxc, and it's going to download and compile it. Yeah, so now it's actually running the CMake script that libxc provides. Yeah, so here's the summary of the CMake run. So we have XML and LAPACK, which is great. Additionally, we also found FFT from the math kernel library by Intel, and we also have ScalarPack provided by Intel. And this is because the MPI compiler of Intel also delivers the math kernel library, which has LAPACK and ScalarPack. And they're actually very fast, so we tend to use them. And with all these, we can simply check the folders we have. So we go to the build directory, and here we find build.mpi. And now we can take make -j, let's say 3, since I have 4 cores and I still want to do some video editing. I will only use 3. And now it compiles a bunch of libraries. So first it compiles this libudft, which is like a library designed around FLEUR, and then it will actually start compiling the libxc. So this is libxc mostly, and since libxc includes a large number of functionals, it takes some time to compile. So now you can see it has finished, and there are actually 2 files. So there's the FLEUR MPI and the imgen. And to test if it's actually working, we can simply type ctest. So now we are running some tests on FLEUR. The 35 tests or so are actually of FLEUR. And after this, there's a lot of libxc tests that we don't want to do. And this is why I included this -i1,35 flag. And as you can see, it seems to be fine. So we will calculate a number of systems, and then we will compare them to previous runs to make sure that what FLEUR calculates today, the current version of FLEUR, is still in agreement with what we have been calculating 10 years ago or so. And now we can have a look at the results. So this is what it did. All the FLEUR tests have passed, and then it starts to do some libxc tests that we actually don't care about. So we'll ignore this, and now you have a running version of FLEUR that is also parallel, and you can use it to speed up your calculation. In this, since you compiled it on your machine, we ensured that the CMake actually ensures that it's tuned to your very machine. So it's advisable to compile the machine on that you actually will run FLEUR on. And with this, I thank you. And if you have any questions, you can ask them in the comment section.